Yes, I have a question regarding to the kidney project. For the kidney, we have a project in my lab for early detection of acute renal rejection after kidney transplant.
Okay.
So we have two aims. First aim is to know if the kidney is rejected or accepted.
Okay.
Second aim is to know the type of rejection.
Okay.
And I discussed this with some physician, and they told me if we make RNA, it can help you to know in a fast way the type of rejection. And I need to ask you, we didn't start, but we just think an idea. And if this can help, how we can get what samples that we need. You told me you can take some from urine or from blood.
So you just need RNA, total RNA.
Yeah.
Yes.
So this is for like what sample? Is it, he told me you can take it from urine or from blood or?
Oh, any RNA is fine.
Yeah, in RNA. And you said it can help you to know the type of rejection?
I'm sorry.
It can help you to know the type of rejection?
That depends on again, so RNA can be sequenced to know which genes in this case protein coding, non-coding access. That's how much you can do. But you have to also keep it in mind that RNA sequencing just taking a picture up to a certain stage.
Yeah.
So more data you have, better pictures that you will take. That also depends on what kind of question you want to ask. You will get millions of different RNA genes.
Yeah.
But which one is specific, that depends on.
We didn't start. This is just a starting idea. This maybe we can discuss this more if we need to know the type of rejection, because we have two types of rejection. It's called T cell
and antibody mediated rejection.
So we need to talk with some people who are expert in genomic and they tell what protein or what RNA or something it can be related to this type of problem.
So it's now trendy to do single cell RNA sequencing. So you can actually take the single cell and then sequence.
Yeah.
However, you have to do a lot of PCR cycle to amplify.
Yeah.
Every PCR cycle you do, you introduce an artifact.
Okay.
As if you do PCR, you actually, if you raise the annealing temperature from 60 to 65, it may work, it may not work. It's the same concept of why is it that there's a lot of things that we won't know.
So RNA sequencing obviously has huge implications for research applications. But what about, is it actually being used on patient samples to help with diagnosis for patients, or is it not quite at that stage yet?
No, not quite as, so I wouldn't say it's not the stage yet, but what I heard from Sigma, the salesperson from Sigma 3 years ago, is that you would not breathe. Physicians, they have money, they order RNA sequences, and they order in the batch of 100,000, 200,000. They get the data. First thing they do is they just store it in the computer, and then they come back a couple of years later, and then asking for a particular question, but they're only looking for this and this and this proteins, and then they don't use the data. So there are a lot of physicians actually did RNA sequencing because they can pay the money. But these data are just sitting on their computer, never sees the light, just because they don't know what to do about it. And even the biologists that I know, they order sequencing from some Chinese company. They got a 500 gigabyte of disk, external disk, and then that was sitting their desk for almost a year. And then they just contacted me whether I can take a look at it. I don't know what they want to do, but it's being used. It's just that you don't know what to do with it.
Yeah, I thought I might be mistaken, but physicians might use some of that data to be able to determine the patient would have certain side effects to drugs.
Yes, that's also possible. And the physicians are now moving towards what we call to be metagenomics. So in your gut, you have different bacteria. So you don't live alone. You have different bacteria that's living. And then they profile for the bacteria. The problem is that it's just like a food chemistry. So the potato chips you eat several years ago thought that it's bad for you because it has certain fats and burned and so on. But what are you going to do? You only want to find out that's bad for you, but you still don't need it. It don't give you the solution. It just gives you, now we have this technology, you detect this bacteria and so that bacteria, but you don't know what to do about it. But it just gives you the more worries. But that's, technology is there, it gives you the information.
But for personalized medicine, I think it seems like that would be quite useful.
So Mike Schneider, he's the professor at Stanford, did this study that was published in Cell 4 or 5 years ago. What he did was that he himself took the blood, urine, fecal matter, and whatsoever. He did everything, proteomics, transcriptomics, genomics, and whatnot, for 6 months. And during this time, he was ill, that had a cough and everything. And then he found out that this bacteria and that bacteria, and this gene and that gene was down. But that's the monitoring that you do. And the current trend, at least for the cancer, is the people start doing the sequencing for the genomic sequence, knowing that aberrant mutations are happening in the cancer. And then they do cancer sequencing. There's a big one in Australia, there's a big one in United States, especially Craig Bender is also involved. But the problem is that you have thousands of samples, and it's the human that who's actually labeling these tubes. And they do make mistakes. And this actually happens in the UCSD San Diego, that you get sequence. But they thought that this is female person, but X chromosome is there. So they have to write an extra program to detect what was the problem, that was the problem, why they have switched to something. So the technology is there, it's still a human error that causes the problem.
Well, that's part of why you're working on it. So you can solve some of these problems. Thank you very much.
Thank you.